the computer, correct.
Okay.
What, sir? What do you mean?
Why it is not going up?
Wait, sir.
Okay, this one.
No, sir. Wait.
So only.
Okay, wait. Don't worry about this. Some money. In others, okay. Next side.
No, sir.
এটা করলে তো নেক্সটে যাচ্ছে গেল নেক্সটে আগেরটা যাবে আগেরটা ইয়ে
ওই মাউসটা ঘুরে দিবে
ঠিক আছে
ঠিক আছে ওকে
and
Mike.
I'm Dr. Desmond, working in the Department of Statistics. And today I'm having the privilege to introduce you with the next speaker. Probably this is one of the best speakers we can have. Also because he is known to keep the students engaged during this lecture, and it is one of the most popular faculty in IIT Patna. So the brief introduction of Dr. Pratibhamoy is that he has done his master's from IIT Bombay and PhD from IIT. And he was a visiting faculty in IIT Kharagpur. He also worked as postdoctoral fellow in Einstein Foundation, fellow in Germany. And he has been the dad of Germany from the duration 2018 to 22. And he is Young Scientist Award winner also in 100th Indian Science Congress in 2013. Above all, he is the top 2% scientist among the world, published by Stanford University. So there are very few mathematicians who are there in this list. So it's really nice to have him here. Today he's going to talk about root finding method. And probably we'll see some of the mathematics to reanalyze what is the mathematical things behind the root finding method. With this short introduction, I would like to invite Dr. Pratibhamoy to start his lecture. Thank you.
hello everyone. I hope you can hear me. So thank you, Ritesh, for this nice introduction. So today my topic is root finding approaches that you can see. More or less, the root finding approaches you have already seen during your bachelor as well as master programs, and we'll be repeating the same things, but not exactly, but vaguely. I mean, I'll pose more questions, and you can have those questions in your mind. You go to your home or hostel, wherever, and you think that those questions, how much it is better. Okay. So we'll try to do as much less as possible whatever you have learned. And we'll pose more questions which you have to. Okay. So let us come to what is inside the root finding methods. So before going to what is root finding methods, let us look into the valid question. Why do I? So this is a natural question. I mean, this question, you'll see that when we are solving a system of differential equations or system of algebraic equations, then we'll be having Ax equal to B form. That itself means, in some sense, you're finding the root of Ax equal to. Okay, so that means if you're having biological network or biological dynamics, you're converting a system of differential equations to system of algebraic equations. So, and then you're finding the root of Ax equal to 0 or X equal to. That's why we need root finding methods. Can you plot any functions by hand or computer? This is a very interesting question. Can anyone tell me what is the answer of this question? Can you plot any functions by hand or computer? Let us forget about the hand part. So can you plot any functions by using computer? So this is a very interesting point. Huh? No, but what about the computer? Okay, so I mean this is very interesting question. Let me use hence those who have done measure theory or numerical analysis or let's say real analysis, you'll see that in fact we can have functions which will not be able to plot by hand also. For example, if it's equal to 1 for rational and 0 for irrational, okay, this function is not possible to plot by hand because rational numbers are countable, but that is infinite. Irrational numbers are also uncountable, and a computer doesn't know uncountable numbers. He only knows finitely many numbers. He doesn't know countably infinite numbers because we are using 64-bit, 32-bit like that. Okay, so that's why these root finding methods are important because we cannot plot a function by using computer. And what does it has to do with the computer? I mean, why do we need to find out the plot of a function? It's simple, because if you can plot a function from R to R, you can zoom that part and you can find out the root. This is the root where it is cutting x-axis. Okay, so that's why if you are able to plot also, it's not so easy to find out the root. Okay, so and the next question, is it possible to check the function is continuous or differentiable or not from the plot? So I should not give the answer, but I should let you think about these questions because of course, more or less all of you know that if you can have a smooth version of a graph, then probably that function is differentiable. And if you have a kind of peak, then that function is continuous, maybe, but not differentiable. Okay, so why do we need continuity and differentiability? Because if you wanted to find out a root of a function, you don't need continuity. Root's definition says if fx equal to 0, set of all x, for which fx equal to 0, you'll be having it. So if you are having a discontinuous function, which is everywhere discontinuous, that is also can have it. Okay, so and why do we need differentiability? Because if you go for Newton-Raphson method, the basic formula itself contains differentiation. So unless otherwise you are ensured that that is having a differentiation, the function is differentiable, you will not be able to use that formula. This is one thing. Second thing, if you wanted to go for convergence, then you need 2 times differential. So we have to be sure whatever function is given, that function is 2 times differential for Newton-Raphson. Then natural question appears, can you give a method from your BSc syllabus for which we need only continuity, we don't need differential? Any method? Anyone? Any method, root finding methods for which differentiability is not required, only continuity is sufficient. Okay, so that because it's not good to give the answer of all the questions. You think, otherwise you'll miss the essence of this lecture. You think, is it possible to find a graph value of the area if the function is discontinuous or what? This one is a measure theoretic question. For example, I take the function fx equal to 0 for irrational, x irrational, and fx equal to 1 for rational. That function is having measure theoretic area 0. Because the measure of rational will be 0, measure of irrational is of course 1, but 1 into multiply 0 is 0. Okay. So there are a lot of things happening in mathematics, and I would rather ask another more interesting question, which is like if we can plot a function and if we can check from the plot that at which points it is cutting the x-axis, then why should I go for root finding methods? Okay, by using the computer itself, we can plot it. Plot, there is a MATLAB, there is a command, plot x, comma, sin x. You plot it and you can check that at which points it is cutting x axis. Then why should you go for root finding? So, anyone who can think of this answer? So again, answer is like if you go for system of nonlinear equations, they are a little bit difficult because there you will be finding the intersection of surfaces. If xy equal to 0, it's a surface in R2. Okay, so there you will be checking the intersection of two surfaces, three surfaces, n surfaces. There it is more difficult by looking into the plot how to find out the solution. Okay, so now finding roots of a linear functions may not be easy. You see that x equal to b is a linear equation. In one day it is x equal to b, a is a real number. In n dimension, a is a matrix, n cross n matrix, b is a n cross 1 matrix. So you are actually solving system of equations. But system of equations solve itself is a big task because you cannot use Cramer's rule. Cramer's rule for 100 matrices itself takes around 100 years. 100 years it takes to solve. Okay, for 100 cross 100 matrices. So that's why you go for Gauss elimination, Gauss Jacobi, Gauss Seidel. Approximation of roots for linear functions are helpful. Newton-Raphson approximate functions by linear polynomials. I'm not sure how many of you know that, but Newton-Raphson, I guess all of you know. Newton-Raphson method. Xn plus 1 equal to xn minus n by f dash. That I'll show you. But what it does is it approximates the function by tangent. And tangent is a affine function, linear function, ax plus b. So that means we are approximating a non-linear function by a linear function, ax plus b. I'll come to that, but this is more interesting questions. Approximating roots of nonlinear systems are not straightforward, as I said, because you cannot plot all the nonlinear functions in n dimension. In 2 dimension it is possible, 3D it is possible, but when you are going for 4D, it is not possible. You cannot plot. So then you have to use a method, let's say Newton-Raphson for nonlinear equations, not for linear equations. Nonlinear equations in Rn, not in Rho, in Rn. Approximation involves exact value. Okay, this is little interesting because you see that when you want to buy a 1 kg potato, you'll definitely not get exactly 1 kg. You'll get 1 kg, 20 grams, something like that. Okay, but if you go to the market, supermarket, they will take the price for 1 kg, 20 grams. They will not take. There are a lot of supermarkets where you will not pay for 1 kg potato price. Whereas if you go for a Sabji market, they will take 1 kg price. So with not press, we're doing the chopping. Chopping means we're not giving the price for 20 grams product. We're just giving the price of 1 kg. Okay. Rounding is a very simpler thing. In fact, if you are using a calculator, there also you see rounding, because your calculator will be having only 8 digits or 10 digits in the display. 8 digits means what? Suppose you are multiplying 3 times pi. Pi is an irrational number. So after decimal, it will never going to end. So if you multiply pi by a rational number or any number, it will always show you 8 digits. But there are countably infinite digits which are not showing. That means there is some rounding going on back side inside the calculator or inside the computer. After that, you are only seeing 8 digits or first 8 significant digits. Significant also you can tell. Okay, so this exact chopping, rounding, exact value very unrealistic in the natural field, but chopping and rounding is very common whenever you are dealing with the numerical analysis, or let's say whenever you are going to the computer or math. Now this slide I have shown previously also. So what is the essence of this slide? Essence says I am solving a second order equation, second order polynomial. Okay, I know what are the exact that everybody knows, minus b plus minus b. But idea is to develop a effective grid which will converge to that exact. Okay, Now, you listen the questions because questions are more important, which you let you think for the research. Questions are, you are having two roots. If you are reducing this problem in iterative form, let's say xn plus 1 equal to g of xn, then that iterative method will be leading to only one root. How to find out the another root? I hope you understood the question. Okay. For example, you have a second order equation x plus bx plus equal to 0, and write down that equation in iterative form. Xn plus 1 equal to g of xn. First question is how to find it out. Okay. Assume that I have given you that iterative form. Xn plus 1 equal to g of xn. Now question is that iterative formula or iteration will converge to only one point. What about the other point? Because they have two roots. Okay. And there is another point which is also to be noted here. That you see that this polynomial can have complex roots also. However, if you are writing it xn plus 1 equal to g of xn form, and if all the coefficients of g are real numbers, initial condition, initial point is also a real number, it will never converge to the complex. Okay. So this is also a lot of interesting things which you are getting, whatever you know from. Okay. So now the question is how to write fx equal to 0 to x equal to gx form. I can have plenty of choices. So I have given you three choices. X equal to this, x equal to minus c by ax plus b, x equal to minus bx by plus c by x. Okay. Which choice I should take? Whether I can choose, whether I can take any choice on. This is also an interesting question. You'll see that we cannot take the choice arbitrarily. You have to take a very specific choice. How to find out the specific choice? Anyone? Listen here on this question. How to find out the specific choice? I have this slide I'm repeating most of. Anyone? That is called fixed point iteration form. So I'm writing fx equal to 0 to x equal to gx form, and I am finding the fixed point of x equal to gx by using some method, and then the fixed point will be. But the takeaway question is, when I'm writing it fx equal to 0 to x equal to gx form, then I'll be finding only one root by using x equal to gx, xn plus 1 equal to g of x. What happens to the other? How to find out that other? Okay, this one will think, because this will help you for CSIR. Okay, so now this whole class, the more intended towards CSIR or GET, or maybe in how to go to the research part. So you see the first one, f is a function from a to b, x equal to j is called a root of the function, j equal to. That everybody knows. But then, of course, there are functions which does not have a root, like fx equal to the power x. And fx equal to x plus 1 is also not having root. This function does not have any root. It depends on what is the domain A which you are considering. If A is a complex, then it has a root, plus minus I. If A is real, then this polynomial does not have any root. Okay. So there is one thing which you have understood, that depending on the domain, the existence of the root is there. If the domain is differing, root may not exist. Okay. So what is the takeaway question? Takeaway question is, we know what is complex number, we know what is real number. What is quaternion? That is one of the takeaway questions. Those who are looking at it. Okay. Next one. Sufficient condition. If A into FB less than 0, then there is a root. Okay. So this is a trick. So you see the definition again. Definition does not include f has to be continuous. Definition of the root does not include f has to be continuous. But I am posing conditions on f is continuous, and if A into FB less than 0 for the existence of the root. That actually means For those functions which are discontinuous, there is no direct way to find out the root of a function. Okay. Second one, it is not necessary that a function will cut x-axis at the root. This is also interesting because for this function fx equal to x squared, x equal to 0 is coming going so y equal to 0 is being a tangential. It is not cutting, it is touching. It's called touching. So that's why this function, for this function, fa into fb will be always greater than equal to 0. It will never be less than equal to 0. Okay. Now, sufficient conditions. This is a very easy questions. You'll get much more tough questions when you'll be applying for CSIR. How to write down fx equal to 0 as x equal to gx form? The one which I was explaining in the previous slide. Okay. So here, the first point is you have to be ensured that this guy is having a fixed. When you are writing fx equal to 0, x equal to gx form, you have to ensure that this guy is having a fixed point. Because if it is having a fixed point, then that fixed point will be the root of x equal to 0. Okay. So what guarantees that it will have a fixed point? The first condition is g has to be a continuous function, and the second condition is g has to be a self map. G of closed interval AB should be a subset of closed interval. Okay, this is a CSIR question. And how do you approach to that fixed point? That is also one idea. So that is leading to a fixed point theorem or fixed point iterative formula, fixed point theorem for finding roots. How do you approach it? So that gives you the next result. If g is a contraction, gx minus gy less than equal to L times x minus 1, where L is less than 1, then this sequence, xk plus 1 equal to g of xk, will convert to a point, and that point will be the root of x. So there are two functions coming. One is fx, another is gx. Fx is the given function, gx is the construct. Okay. Now, what is new I am getting here? The new point which I am getting here is this line. For any starting value x0, this will be converged. If you look into the Newton-Raphson formula, there is a condition given. Initial root should be closer to the initial root approximation should be closer to the. But here I am not saying. I am saying that you take anything, it will converge to. Okay, this is one of the initial. What is the compensation which you are making? Compensation here, what you are making is G should be a left state function. This is called left state. G should be a left state function, and G has to be a self map. G of closed interval AB should be a subset of closed. That is difficult to find. Okay, this is an example where we have constructed this G from this F. F is given. We have been asked to find out the root of F, and we are constructing G such that G is continuous and it is the self. Okay. Now, very easy question. Anyone can answer. Suppose G satisfies this condition. Can I say that G will automatically continuous? Anyone? This is a very easy question. Yeah, BTech guys will be able to answer. Suppose G satisfies this condition. Can I say that G will be automatically continuous? And the next question is, can I say that G will be also automatically differentiable? This is the easy question. First question answer I can give. So if a function is left shift, it will be automatically uniformly continuous. So it will be continuous. Okay. So next question is, can I say that G will be also differentiable? What is the example? You take Gx equal to mod x and apply triangle. Mod x is not differentiable at x equal to. Okay. So now this is little interesting. Maybe the second one, not the first one. So we can have nonlinear function, okay? Polynomial, and as long as it is a polynomial, we can work on the existence, uniqueness, and lot of things. How do you know the existence? Because fundamental theorem of algebra says that if you are having nth order polynomial, then they will be having n roots in complex, not in real, in complex. Okay, that is the algebra. And how do you know that in which side the root will lie? There is a theorem called Descartes' rule of side. You find out f of 1 plus, you have 1, f of 2, f of 3, f of 4. Check the change of sign, and from there you can find it. Okay. And how do you know the location of the distinct roots? This one is little you have to go inside the algebra part, classical algebra part. There is something called Sturm's theorem, through which we can find out the location of in which interval the root is lying. Okay. So these three are only available for polynomials. But I can have function which is not a polynomial, like x sin x equal to x sin x is not a polynomial. Okay. So now question is, how do you know? So let us start with bisection. Bisection is a simple everybody knows. You find out you find an interval where the root lies, and then if into fb less than 0, then there is a continuous bisection. Everybody knows. Okay. But what guarantees that there will always exist one? This is the famous interview question. How do you know that bisection method converges? PhD interview question. So that is also can be answered by first year BTech real analysis class. That is called Cantor's theorem of nested intervals. Anyone knows? Anyone heard about Cantor's theorem of nested intervals? So you are taking an bn, an interval, and if the length bn minus an goes to 0, then intersection of closed interval an comma bn will be non-empty. That is called Cantor's theorem. Okay. Based on that, we can find it out the existence of the bisection. Okay. So now, what is the take-away question? Take-away question is very interesting for research. See, the whole idea of bisection is only one dimension. Fa into Fb is less than 0. Okay. Suppose Fa is not a real number. Suppose Fa is a vector and Fb is a vector. How do you bisection? What is the meaning? Meaning is I am taking f is a function from R to R. Now I am taking a function from R2 to R. That also can have a root. Definitely it can have a root. Surface. How do you use bisection? We think. Okay. It may be possible if it's a function from R2 to R, or if it's a function from R2 to R2, how to use the bisection. Why the problem is appearing? Because 2, 1 and 1, 2 is not comparable. R2 is not comparable. R is comparable. Two numbers I know which one is bigger, which one is small. But in R2 we cannot see. That's why this question is interesting. Okay. Newton-Raphson method. Existence is fixed point theory. What is fixed point theory? Newton-Raphson method says xn plus 1 equal to xn minus f of xn by f dash x. This is the formula. So now, how do I get the fixed point? Because I'll write down whatever is in the right hand side, then I'll write as gx. Gx equal to x minus fx by x. So it's a then you come to fixed point theorem and you check that under what condition it is. Okay. So bracketing methods. I was telling you what are this bracketing method? Bracketing method means if there are two initial gates, and if you are sure that between two initial gates, root will always lie, then that method will always work. But the convergence rate is. So what are the methods which we know as bracketing methods? One method we know is, of course, bisection method. I'll give an example. I'll give you a question that secant method, is it a bracketing method or not? Bracketing means I'll give you two initial gates, root will always lie between those two gates. Okay. Secant method is a bracketing method or not? Okay. Open method. Open method means what? Open means I'll give you only one initial gates or maybe two initial gates. But root may not lie inside those two, may lie outside. So Newton-Raphson is an open method because I am giving you only one initial case. You don't know in which side you have to go, left hand side or right hand side. It's an open method. It says that convergence is not assured because I don't know the initial case. But if it converges, it is faster than everyone. Let's say bisection. Okay. I'm not going into the theorem, but I'm going over the heads kind of thing. Now, direct methods. This slide is not much interesting, but there is one takeaway from this slide is what do you mean by direct? Direct method means I can solve it by hand, roughly speaking. Okay. Now, for polynomial case also, it is not possible. I guess all of you know that there are polynomials, let's say fifth order polynomials, which I cannot solve by hand. There is no direct method to solve a fifth order polynomial. There's a famous theorem called Galois theorem, Galois. So we said that if you are having a fifth order polynomial or more than fifth order polynomial, you cannot solve it. Impossible. There is no direct method through which you can solve it. So that is the takeaway. So there are no direct methods for solving higher degree polynomials, but less than equal to 3 it is possible. This is only one takeaway you can take. And iterative methods. What are the positive parts? Positive parts are iterative methods are useful in the sense that you can get an approximation of the exact. For example, you take x equal to b system, linear system. X equal to b I can solve by using Cramer's rule. X equal to b I can also solve by using inverse. X equal to inverse b. But what is the problem? Problem is if A is a 100% matrix, it takes years or maybe 100 years to find out the inverse of the matrix. That's why we're coming to Gauss elimination, Gauss Jacobi like that. And those all methods are iterative methods. Means you can only find out an approximation, not the exact value. Okay. So similarly, for one-dimensional case, A from R to R, those things are bisection. It's an iterative method. Newton-Raphson, this is also an iterative method. First term, but A should be differentiable. Second, I don't need F to be differentiable, but I need F into F being two iterative cases. Second. Okay. Okay. So now this one all of you know. I'll just pose the questions from this slide. This is the derivation of the Newton-Raphson for functions from R to R. It's an interesting thing, huh? R to R. First question: if the function is from R2 to R2, which side will break down? There are several parts which I have written. You have to think that which line will break down, which line will not work. Suppose I am giving a system X equal to B, or in nonlinear system, which line will not work. Okay, this is one. So let me just explain you what is the one-dimensional idea. So I am assuming Fx equal to 0 is having a root. That is the initial case x0, and x1 equal to x0 plus h. That we know. And I am finding the Taylor series of f of x0 plus h. I am taking only first two terms. This is the one. This is equal to 0, and finding the step h. Based on that, I am writing x1 equal to x0 plus h, and by that way I am deriving the formula. Okay. So now, question which I have posed. Suppose f is a function from R2 to R2, which one will break down? Okay. So more interesting question is, suppose f is a function from R to R. F's derivative is a function from where? It's a function from R to R. That you can check, roughly speaking. But if f is a function from R2 to R, you check that its derivative may not be a function from R. It will not be a function from R. It will be a function from R2 to R. Okay. So that means this derivative itself is a vector, and immediately you cannot divide it when you are going from R. Okay. This is a standard thing. We approximate a function by tangent in the Newton-Raphson method. So let us skip this one. Okay. So now this algorithm, let us come. So I'm explaining the difficult parts in the algorithm. Okay. So in Newton-Raphson method, we know that we have to find out the derivative of function. That is obvious because we have to find out the formula. To find out the formula, we have to put it in. Okay. So we found out fxn, f dash xn, and formula is also there. Question is, where will we stop? There are two interesting questions. One question is, suppose you don't know the convergence, where to stop? Because if you don't know the convergence, it will go away, it will go somewhere, and you don't know that is the root. And second point is where to stop, because this sequence is in general infinitely numbers. You have to stop some. How to stop? You see that there are three stopping criteria given. One is fxn less than epsilon. Epsilon is the we call it tolerance. Epsilon equal to 10 to the minus 10. Okay. So if you take this has 10 to the minus 10, I will show you none of these three stopping criteria actually leading to the convergence. But numerically, when we are writing code, we use one of this. Okay, so we are going reverse. We are using something in the computer, but we are saying that whatever we are writing in the computer, that may not be correct. So how? So one is fxn less than epsilon, because suppose epsilon is 10 to the minus 10. F of xn, if it is less than 10 to the minus 10, it does not imply that it is having it. It may not have it. So you just take fx equal to 10 to the minus 10. 10 to the minus 20 constant function, it does not have it. Okay. So the first one itself is not correct, but we are using in the code. Second one, xn plus on xn minus xn by xn less than xn. What does it mean? One of the idea is if xn equal to 0, then dividing something by 0 itself is invalid. So this also cannot be, but still we are using it in the computer when you are writing. Second one is n greater than some number, let's say 1 billion. Of course, we know that if it goes to 1 billion, it does not immediately converge, because in 2 billion also it can be outside of the root, root interval. Okay, but still we can say that these are all the approaches which we can use to approximate the roots. Okay. Okay. So now this one very interesting. Hardly someone will feel any interesting part inside this slide, but I'll tell you what. I have given you a formula. Happened to be a Newton-Raphson formula. Suppose I am taking xn plus 1 equal to some function of x. Not the Newton-Raphson formula, some other function. Okay, and I am giving you this data. x1, x2, x3, x4. You wrote this data, you submit it to a journal. Okay, suppose I am the reviewer. Now, as a reviewer, by looking at your data, without writing the code, how do I be able to check that this result is correct or not? You understood the question? You have given me data, you have submitted to a journal, I am the reviewer. Of course, I will not write down the code. Obviously, but by looking at the data itself, I can tell you that this paper is correct or not. That means it is going to be a correct one or it is fully wrong. That itself I can tell. How do I be able to tell? You think, because as a reviewer, suppose I am an editor. While looking into the problem itself, I can tell you this is not correct. Or this data you have manipulated, you have written by hand, you didn't find out by using computer. That is possible. In some places it is possible, not always, but in some cases, those who are a big numerical programmer, they don't write code by themselves. When they are reviewing a paper, they just simply look into your result and they will tell that it's not correct. How you think? Okay. Okay. This one I'll not. Let me just go through this theorem again. So this theorem gives a same order convergence. This is the convergence. The observation is the formula takes only one derivative, x1 plus 1 equal to xn minus fn by f dash xn. But the theorem convergence result requires f to be 2 times differential. F is in C2. So that means when you are going for theory, you need more smoothness, more differentiability than what you are having in the formula. This is one thing. This happens several times. Everywhere else, everywhere in the numerical analysis, you will see that bisection method declares continuous, but when you are going for the convergence, you declare more smoothness. This kind of things you will see in the literature. So I have the 15 minutes. So now this is one of the questions which generally comes, but 2D version is more interesting. So here, xn plus 1 equals the Newton-Raphson formula that everybody knows. So question is, can you pose a condition on F under which this Newton-Raphson formula will be always convergent? So when I was asked to set up the paper of BHU chemistry entrance, I set up this question. So let me just explain this question. We know that Newton-Raphson formula may not converge. If the initial guess is closer to the root, then only it converges. Okay. In fact, there are functions for which it doesn't. So question which I asked is, can you pose the condition on the F? So I have to give 4 conditions, out of which one has to be satisfied. Only one can be the correct answer. So can you pose a condition on F or on its derivative so that this Newton-Raphson method is always converge? So this question I posed in BHU entrance, Banaras Hindu University. So idea is you write in fixed point form, xn plus 1 equal to phi of xn form, and where phi is equal to this one. That means this right hand side part, this one right hand side part, and then you take the derivative of phi. That has to be a contraction. Phi dash x should be less than 1. If it is contraction, if the function f to be like it satisfies this condition, then Newton-Raphson method will be always convergent under any initial. Okay. So do you need some restriction on the domain phi? That I'll leave it for you, because I need phi also should be a self-map. Once phi of closed interval AB is subset of B, phi should be a self. Okay, so now there are a lot of things to explain, but let me skip this one. Okay, so let me just go from the formula point. So all of us know that Newton-Raphson method is a second order method. So can you give me some functions where the order reduces to first order, or the order converges increases to third order? This is a very common question in GATE. The answer is anyone who knows the answer? If you are having a GATE, then you'll get this 35%. So this is a very common question in GATE. I think last year was to get GATE. So the answer is if f is having multiple roots, if f is having a multiple root and we don't know the multiplicity of the roots, then the order will reduce to 1. And if you know the multiplicity of the root, let's say there are 3 times 1 root is appeared, let f is equal to x cube. And if you take that multiplicity here, multiply that multiplicity here, then the order will be reduced to 2. Okay. So the last question which I have posed, that can you increase it to 3? Can you have a equation function which will increase second order Newton-Raphson third? Okay, so observations are trivial, but this slide is more. I should motivate also on the research side, research part. So this slide is more interested on the research part. Okay, so very easily let me explain. So these are two functions. As you can see, it's a very simple function. First one is an equation of a circle, right? X square plus y square equal to 1. And second one is an equation of ellipse, right? 5x square plus 21y square equal to 9. Okay. So this happens to be that these two functions are crossing one another by 4 points. If you draw a circle and if you draw an ellipse, then they will cross at 4 points. Okay. So that means f1 equal to 0, f2 equal to 0 having how many roots? 4 roots. Because I am finding the intersection of a circle and ellipse. Okay. So question is how I have to find out 4 roots, which will satisfy f1 equal to 0, f2 equal to 0. The answer is how to question is how to find out the roots by using Newton-Test. You understood the question, right? You are having a circle, you are having an ellipse, they are intersecting them at 4 points. How do you find out those 4 points? By Newton-Test. So this is the formula, as I was telling, that in this case, you see that all those 4 points are vector form. They are not real numbers because they are the coordinate in R2. Okay, that means the root will be also in R2. So that root is written as x vector. Okay, so xk plus 1 equal to xk minus fxk by f dash k in R. So here what is happening? Fxk is capital F, but by f dash is k. So derivative of a function from R to R, when you are extending it to R2 to R2, that is called a Jacobian. Either gradient from Rn to R, or when you are going from Rn to Rn, that is called a Jacobian. Okay, so this Jacobian is called Jk. Okay, I am assuming that Jacobian is invertible. That means Jk inverse exists and unique. So based on that, you are able to find out a vector formula xk plus 1 equal to xk minus Jk inverse, which is the 1 by f dash xk into fx. So this is a path through which I can find out the Newton-Raphson method for nonlinear surfaces. Nonlinear surfaces, not functions. I'm working on the surface in R3, Rn. Okay. So now, what is the condition under which this Newton-Raphson method will converge? Okay. One condition is this Jk inverse. There are plenty of norms I am having in Rn. So I need the Jk norm should be less than. Or you can take the spectral radius should be less than. Okay, this is a very interesting slide, because this slide only you need during your research. Okay, other parts are just the basic. Okay, this is the more important slide because we are going to the surface, we are going to the Rn in dimension. Okay. So now forget about these parts. This Newton-Raphson or linearization methods also we can use when you are solving a nonlinear differential equations. Here I have y dash equal to fxy with y at 0 equal to y star. This is a first order initial value. Okay, I can use this linearization technique to find out the solution of this by using backward Euler. I hope you know what is backward. Okay. So here what I'm doing is I'm linearizing this nonlinear function fxy by this technique. This is the initial guess yj plus 1s, and this is the approximate solution of yj plus 1s plus 1. After linearization, I have approximated this quantity to this. Okay, then we will be able to find out the solution yj plus 1s plus 1 by using some iterative technique, which will take this one as the initial. Okay, this one is one takeout. Okay, how to solve system of nonlinear equations by linearization. And this is one of my research papers, single author paper, because this is the last slide almost. So here I have shown it already. So this one is having, this is a nonlinear equation. There I am having two unknowns, u and lambda. So we can still use Newton-Raphson method which will come out to be of this form. Iterative formula will come out to be of this form, and two initial guess. So that guess is taken like this one. Both the guesses are functions, not points. Both the guesses are functions. It is a function, not a. In Newton Raphson, you are having a point as initial, but here it is a function. Okay. So after that, my research was to develop a adaptive mesh technique, which will converge to the exact solution. So that is on uniform mesh. If you use MATLAB, uniform solvers, partitions, it is diverging because errors are not decreasing as the number of partitions are increasing. You see 0.115, 0.1. So errors are increasing when I'm increasing the number of partitions. But in my proposed case, it is decreasing. Okay, this is one of the single author paper published in J-Cam. There's a highly cited work of mine. So there I have shown that proposed a method, partition points, non-uniform partition points, where I can use linearization technique to approximate solution. Few of the questions you can pose, you can take these questions in your room and think about the answers also. I have given the options also you can think of. And almost time is over now. Thank you. You have to take the questions. This is the question. If you want to have.
The forum is open for questions. If you have any query, or if you want to join in his group, any kind of interaction is welcome. So you can my everybody can. Your second side, you have given that is equal to minus BAX squared by cannot X.
Cannot?
So your X is equal to minus C minus BAX squared by. Do not define that. If P is equal to 0, it cannot take.
So those conditions are assumed. For example, X plus B equal to 0, then the second one is invalid. Third one is invalid if A is equal to 0. Those things are I have assumed that they are not. And B is also not 0. So if your B is equal to 0, then you know that the first one is invalid. It's going from second one or the third one. And then from second one or third one, you derive an equality form.
When you are writing it, not correct.
So it is assumed that the numerator by denominator parts are not. Otherwise, the one of them will not be there. One question. We can speak to the notes.
That's very nice, sir. I don't have any question. Can you recommend any human command for me?
Okay, so one book which is now not that much having mathematics and is popular in whole India, sometimes. That is Zheng and Engg. I think Arosha or New published. Very famous in North India. Zheng and Engg. All of these three papers are from IIT. That is not having much mathematics. But if you go for mathematics point of view, like the slide which I am showing, where Jacobian is appearing, for that there is a book by Sully Myers, Henry Sully and Richard Myers. They are from Oxford University. That is Introduction of Numerical Analysis. That is a book. Edition book is available. PDF file is available in India. But China English PDF file is not available. Indian book is not available. Then can you write a book? So 15 minutes, I don't know how come Aman came about 15 minutes. So it's maybe he is available with partners. Okay, so let me just last slide. So so Shishkin mesh is something. Suppose you are having a problem whose solution is having unbounded elements. Solution can have unbounded elements. So if your problem is having two variables, let's say one is x and another is a parameter, let's say here. For example, in this case itself, solution is u that is depending on independent variable a, and in addition to that, there is a parameter epsilon, and epsilon's value is not. Okay. Then in this case, solution you will see that derivative will be unknown in terms of epsilon. Okay. Now, question is, this kind of functions will be having a boundary layer kind of solution varying rapidly in a small region. So, can you provide a partition point where the partition points will be dense to the region where the solution is varying rapidly and not much dense to outside the region? That is called an adaptive. Shishkin has proposed one mesh, that is a piecewise uniform mesh. So that is a uniform, piecewise uniform. In throughout the domain, it is having only two pieces, two uniform meshes. So that is called Shishkin mesh that he has proposed. And those meshes are very popular in boundary layer theory and similar part of analysis. So, this one is having a Shishkin mesh. You see that blue color line, which is matching the pink color line. Pink and blue are both are matched. So if it is if you zoom it, you will see that this is a straight line. It means with a uniform mesh kind of uniform in one side, uniform in the other. It can be full uniform in both the sides throughout the domain itself, but it is uniform in one side, uniform in the other. So uniform Shishkin mesh not giving you optimal, giving you color. Don't have it. Okay, he can hear me. He can hear.
Okay, with this we this kind of session of this talk session will continue. And I'm thrilled to see the slides because it has been a long time since myself studied the numerical analysis for good finding methods. But if you look at from the machine learning point of view or data science point of view, you will recognize from the last slide, the second last slide, when he was talking about the vectorized products return after method. You will realize that how these root finding methods are implemented in deep learning framework. So in the deep learning framework, where we want to optimize the surface of the loss function, we go to the root finding in order to find out the root of that loss function. And so far, people have not come up with a very, very efficient method. The Newton-Raphson method, which is second order, is still not very much applicable in learning aspect. But you have gradient method. So in a nutshell, root finding methods are very, very, very useful if you want to work on them or if you want to use them in your work. With this, I would like to close this talk. Thank you, Pratibhamoy. And thanks. So can we have a round of applause for the speaker?
From here only that foreigner is there. No, no, no. Oh, Mike Meylan is there. Now, yeah, ready. Yeah, perfect. Oh, that is your list. Fine, great. Great. That is your list. So he's on video. Yeah. Yeah. Am I audible to you?
Yeah.
Hi.
Yeah.
Yeah. So this is Ritesh Dubey from Asaram, and I have the responsibility to introduce you for this talk. So
We'll just start sharing my screen if it's all right.
just a minute, let me say something about you as asked by the organizer. So
Yeah.
next speaker is Professor Mike Meylan. Mike Meylan obtained his PhD and PhD degree from Chicago University, New Zealand in 1991 and 1994. And he held appointment at Mishra University, University of Auckland, currently at the University of Newcastle, Australia. He is in the wave theory, especially in the coupling of the he has worked extensively in linear aerodynamics, principally in relation to wave scattering in frozen ocean. He has also worked on applying the theory of generalized and the singularity question matter in two problems in aerodynamics. Today we will talk about time-dependent problems in wave itself. And with this thought introduction, I request Mike to share his screen and start his talk. Yeah, Mike, can go ahead.
All right. How do I get this to be full screen? Full screen. All right. So hopefully you can see and hear me.
Yeah, it's coming. Yeah, it's fine.
Okay, brilliant. Okay, thank you for the introduction. So that's great. That it's all working because I'm in the hotel, so I'm slightly worried about how good the internet would be here. All right, so I'm going to talk about this problem of time-dependent wave scattering. So we'll try to explain a little bit of what it's about, and I'll illustrate this with some examples. We'll see how we go for time. I will like to talk a little about the smooth particle hydrodynamics method, which is a very powerful method for solving nonlinear fluid mechanics problems. But I'm going to start out with some rather simpler, well, perhaps simple is not the right word, but linear problems, simpler models for fluid. And these are some pictures here that I'm sure some of you have seen before about waves in ice, which is one of the main things that I've spent my career modeling. I wanted to show you this. I don't know how well this will play on Zoom. There's always a bit of a danger with these movies. We'll see what happens here. This is not a good start. Let's see what's happening. Let me see if I can get this. It'll be very annoying if this doesn't work. Disaster, in fact. Was playing before. Okay, what to do? See if these other ones, if these movies aren't going to play, then this would be okay. That one's ordered. So this is a great movie. It's not. I really wanted to show you it. I can perhaps just try to show it directly. See if it'll play here. All right. I'm not sure that you can see this movie or not. I've lost the I'll play the movie anyway and we'll see how we go from here. We'll have to live without it. You didn't see it. I can't see the yeah, it's a bit of a problem. The Zoom and the might need a new laptop. Clearly need a new computer. It's not powerful enough. All right. I'm hoping you're seeing a movie of a plate of a ship going past. And then we're going to see it break up the ice here. Waves propagate into the ice and break it. This is a really interesting problem because the boundary, the waves are fairly linear here, but the boundary condition is changing constantly as the problem evolves. So you imagine trying to model this, you've got this cracking of the ice. So you've got a wave field inside the ice, but the material properties are changing continuously as the ice cracks. So it's kind of a difficult problem to solve, at least using some of the tools we've got. So this is a really interesting problem for lots of people who are interested in how this waves break up the ice. There's a beautiful movie of it. All right, and the ship continues to crack. The ice is very fragile and it gets cracked up. There's a lot of mass in this, like why does it form these shapes? How do these cracks propagate? What distribution do you get of sizes, all kinds of things? All right, let me go back here. Okay, so I'm hoping you saw that movie. All right, here we go. So I'm going to talk about this thing called the generalized eigenfunction method. It's quite a difficult, quite mathematically challenging method. It's very general and it's not super well understood. It's not in any textbook that I know of. There's not really a clear explanation anywhere that I've ever seen or read. So we're kind of in this kind of gray area with this idea where you know, it's beyond Wikipedia and it's beyond YouTube, a long way beyond those things. So but it's actually not that hard to understand it. So basically it just generalizes everything in maths is a generalization of a previous idea. So this is the idea that it generalizes this problem that everyone should have met, where you've got dx dt as mx, where x is a vector. I probably should have used bold here, and m is a matrix. And we're assuming that the matrix is self-adjoint, has a nice has eigen vectors and eigen values, and they're, in the case of a self-adjoint matrix, they're orthogonal. And you can get this expansion for the solution written as this in this form here. It's perhaps not the easiest form to understand the theory here, because what's going on here, if you think about it, it takes this inner product is actually a matrix multiplication. You might remember this, and then you raise the eigenvalues to a power. This is sort of a diagonal matrix. Got to sneeze here. Oh, all right, sorry about that. this is a diagonal matrix, and this is another matrix. It's sort of actually the same matrix you used here. So it's you write the solution down, and it has this advantage that the solution's accurate for all time. It doesn't have any time stepping in it. You'd be silly to try and solve this problem by any other method. You certainly wouldn't want to use Euler's method or some time stepping method. So there's this structure here. And the question is, how far does this generalize? And it actually generalizes a long way. Here's the case if you get a second derivative here equals minus m. This is something you wouldn't see. So this case is more like our wave equation. In fact, this is the wave equation, because the m here, this matrix, we can just replace with minus the Laplacian. And minus the Laplacian is a positive self-rejoin operator. And we get right down the solution in this form here. So it starts to get a bit weird because you have causes and sines of the eigenvalues, but that sort of makes sense, right? Because you differentiate this twice, you're going to multiply by lambda squared. All right. And you're going to get a minus coming from, if you differentiate cos, you get minus. Okay, and the same with the sine here. And you have two initial conditions, the value of that function at 0 and the value of the derivative. Okay, so this probably could appear in some course on differential equations if you had it, if you wanted to do it straight after what you've just done, but people would find it a little bit, too much or something like that. And of course, you could write this as a double system with two matrices here. You could double the size of the system and have just a single matrix. All right. So let's just consider here this super simple problem, which is the wave equation with variable, because we just have the wave equation, it's going to be really dull. We have a variable thickness. So and you can think about this in a few different ways, but from the water wave perspective, it's where there's a change in depth. You've got a tsunami wave, some sort of shallow water wave, and it's encountering a change in depth here. And it has some initial conditions. So we're not interested in the solution, we're interested in the time-dependent solution. We're going to start it and see how it progresses in time. So now we can write down the solution in this kind of form here. So we're assuming that we can we've got boundary conditions at the edge. So at the ends, there's no flow. There's no flow, like it's like in a basin or something like that. So we're looking at the sloshing modes in a basin. And we can write down the solution exactly generalizes what I just wrote before. I've gone up in 3 steps here. And then I've perhaps got, whether it's confusing or not, perhaps I should have been consistent, but I've changed the eigenvalue to be minus lambda squared. So I've just got a cos of lambda here rather than having the square root. Okay, because I've got this minus lambda squared. These are the eigenfunctions. Okay. So that's no problem. This is all, this operator is compact, it's Sturm-Liouville theory. This is all exactly understood. Okay. This is the Sturm-Liouville problem solved. Okay. You can see that's exactly the form of the Sturm-Liouville problem, isn't it? This is exactly the form. You have the derivative, then some function inside it. Okay, hopefully this is going to play. Please play for me. No, it's not. It's going to be very frustrating if none of these movies work, because it's sort of the talk is told. I can't really explain the talk without these movies. See what's going on here. It might play better in this mode here. It played before, didn't it? I just tested it and it played. Then I restart this program. That's all right. All right, sorry about this. Shut down every other program running. All right. That was actually about to play here. Here we go. Brilliant. All right. I just think something goes on with that full screen mode. So I'll just have to get the presentation in this mode. Okay. It's a little bit annoying, but we'll cope with that. Maybe shut this down. All right. So you see here what happens is this is the change in height, right? So you get some started with some initial condition that you prescribed, and you allow the system to evolve forward in time. And then at this thing here, it hits the walls. So this is a simulation of the solution, right? It's like waves on a string, but you've got some much more complicated waves. So you've got these modes of vibration of the system, and you've expanded it, and you can write any initial condition in terms of those modes of vibration. So what happens if we go to a infinite string? This is the next step. Basically, the whole idea is encoded in this, what I'm about to tell you. So we want to allow, instead of having a wall here, we want to allow the thing to just expand out forever. So what's going to happen is that wave's not going to hit the wall and bounce in, it's just going to disappear off. So how can we do that? What happens now is that there's no sort of eigen modes, there's no fixed frequencies of vibration. Any frequency of vibration is allowed. And we need to impose, we've got this boundary condition at infinity, and we need to impose some condition at infinity. So what happens is when we ask the same sort of question again, we end up with every lambda is allowed. So we've got to integrate over R plus. So we're allowing everything. It's sort of, we've gone from the Fourier series to the Fourier transform, essentially. And we have to have some incident wave. So for example, we have an incident wave coming in from infinity. We need some boundary condition at infinity. So we have an incident wave plus a reflective wave. And then when we do that, we end up finding that if you remember from your Fourier series, you've got, I should have written this down actually, you've got e to the I omega x, or e to the ikx times e to the ik2x or something. You end up with a delta function, this very strange relationship involving a delta function for the Fourier series, for the Fourier transform. Exactly the same structure appears here. That's why it's called a generalized it's like a generalization of the Fourier transform essentially. And you even end up with 2 pi here. Okay, you end up with, you've got waves coming from both directions, so we've ended up allowing that. Okay, we get another term here from the directions. It's not super important, but they normalize. This is the most tricky part of this whole method. There's no, the proof that that's true is, to best of my knowledge, I've never read or, and I've certainly never understood it. But you can kind of show it formally, but it's a very tricky idea. Even these way these delta functions appear is in the Fourier transform is really tricky anyway. But that's the case. So that's probably, this step here is the most difficult bit to understand. Okay, most unknown. And this is where we're a long way from a YouTube video or Wikipedia at this point. So here's the formula though you get, and you can write it down, and it's an integral, but you know, integrals aren't that scary. And in fact, the integral, when you do it numerically, turns back into a matrix. So strangely enough, you end up back exactly what you had before, right at the start. You start with your vector, you multiply it by a matrix, you multiply it by a diagonal matrix, and you multiply it by another matrix. And that other matrix is the transform of the one you started with. You can sort of see that here. The same functions appear inside the inner product as outside. This is a neat formula, but it doesn't show you the matrix multiplication. This is matrix multiplication, and then this integral is matrix multiplication. And then this is the solution here, and you can see it's quite cool because it's exactly the same as the other solution at the start, because the wave doesn't know anything about the wall. So in some senses, it's like imposing, but of course, once it hits this wall, we've just chosen to plot it in the same domain, it just disappears off, and you get the solution like that. So and you can start to see here some kind of interesting properties that you get this persistent wave here, and that somehow that's come out of this mathematics. So you can sort of imagine these high law pumps, they track some mode sort of between it. it slowly radiates energy. It's perfectly designed. This is a fantastic way to analyze systems that have this kind of persistence and then this radiation. They have lots of names. They appear all over the place. Like they're called near trap modes, they're called leaky modes, they're all the same thing. And there's nothing special about this. I just decided to solve the wave, this particular wave equation. There's nothing special about this. It can it's called the generalized eigenfunction method, but it generalizes wildly. There's no end to where you can take it. Okay, but it's interested in solving time-dependent problems. You start with some initial condition and you march it forward in time. All right. So now we go on to some other problems. So, and so all of the equations just mimic, the structure is just mimicking what we saw before. So here you have this wave equation here, dt squared eta is Laplacian of eta. So this is just the wave equation in some bounded domain. So in a bounded domain, you know that this has discrete spectral points and you can expand in terms of it, and there's the solution. So these would be like the modes of vibration of a drum, for example. Some of you will have, a lot of you will have solved this problem at some point. You might have forgotten about it. Some horror stories. It was separation of variables and you got Bessel functions. And you calculated the modes of vibration of the drum. Maybe the professor said to you about how the modes don't line up. So that's why drum's not very musical. Or that's a bit dangerous to say that. Some of you might be drummers, but it doesn't produce that kind of beautiful resonant sound you get out of a violin or something. There's a reason why most musical instruments are one-dimensional, because the frequencies line up in a very simple way, like a string. But here they don't. Finding these lambda cases about you got to find the zeros of some Bessel function. But you can write down the solution here, and you probably never went and ever tried to compute it. You just calculated the modes, and that was done. You never tried to actually, and you certainly, if you write this formula down, you never calculated it. I'm not sure. So what happens if we go to the opposite problem, where instead of having a drum, we have everything but a drum? So we've got an infinite domain. Well, then that we go to this generalized eigenfunction method. So we're allowing waves to come in from all, we've got to have waves coming in from different directions. And this is like this is commonly just solved just as wave scattering problem. And there's a jump here. If you ever analyze these in a maths course, you'd suddenly just forget about the idea of solving the time-dependent problem like you did for the drum, and you'd go and just solve the problem for the frequency domain. But you can actually do it using this generalized eigenfunction expansion. Rather, to the best of my knowledge, so it's a very simple problem. If you think about it, everyone learns, it's rather strange, everybody's learned how to solve the problem of, and everyone's a dangerous statement, but lots and lots of people, there's probably people studying it right now, writing an assignment on the vibration of a drum. But the opposite problem, how to solve the time-dependent problem in the exterior of a drum, that's problems, to the best of my knowledge, has only been solved by one person, and he's speaking to you now. So at least numerically, I mean, it's, and using I should say, with the proviso, using this kind of expansion method, just like we did before for the drum. Okay, so it's not super important, all the details of it. You have waves, incident waves that are Bessel functions. You can have plane waves, but it's usually easier to solve in terms of Bessel functions plus some scattered wave. And then these things normalize exactly like you'd, in terms of a delta function. And then you've got to find this normalizing constant. Like I said, that's always the trickiest part. And it's the strangest part of it, because there's this theorem that tells you how to calculate it. The theorem was written down. Never seen the theorem written down. It was told to me by someone, sort of like a mystical, math starts to get a little mystical at some point, but the theorem's definitely true. I have no idea how to prove it, but, and I'm not sure that the theorem's been written down in its generality. It just seems to apply every single time you meet it. So the proofs of it probably weren't for it. But anyway, it turns out to be 2 pi over lambda. It's something, I can kind of explain why you'd expect it to be that, but essentially you get the same answer with or without the scatterer. Some sort of compact perturbation theory of a continuous operator or something can't break the spectrum. There's some notion like that deep in mathematics somewhere. But it's very hard to extract that theorem out for people who actually want to do something like ourselves. All right, and there you go. There's the formula for this thing. It says surprisingly not at all well known, that probably because it's only been written down by me. I have no idea if it's. I certainly didn't. If it's been written down by somebody else, it was. You know, I didn't know. I don't know anything about it. This is where it starts to get. Maybe this is a step too far in terms of the talk. No, the talk might have been a step too far. I wanted to talk about something kind of complicated. So I did this research a while ago, and then I decided it was too hard, and I started doing something easier. And of course, I got a lot more citations and all of that stuff. So, because easy problems tend to get cited a lot more than hard problems. But I've kind of decided to come back, and I'm not got long to live. Being 53, and so you realize 20 years ago. So I wanted to try and finish some of this stuff, and explain it. But and hopefully, if we go on, other people will keep working on this or something like that. Other people will appreciate it and try to explain it to people, at least get them interested in it. But it turns out that you always end up with these linear problems with the structure of a matrix. I don't know why I've written a matrix A times plus A times F, why I've introduced this identity matrix. You do always end up with the structure, but it seems to only just confuse it. So you always end up with this structure in these problems. It's incredibly common. Anytime you got it, lots of times you have to invert a matrix. And in these problems, people they scan across a range of frequencies. So they look for frequency 1, frequency 2, frequency 3. So they have this parameter, which I've called K, which is really the frequency. And so you end up with a matrix that depends on the frequency. You're sort of scanning across. So then all the rest of the problem doesn't change. The obstacle becomes the same. The material's the same. The properties are the same. It's just the frequency you're varying. So you end up with a structure. You have to invert a matrix, and the matrix changes with frequency. So you end up down here with a structure like this. This is sort of, but what turns out that if you stop and think about it for a second, this M is going to be analytic. This is a slightly weird idea, but what that means is it has a convergent power series. You can differentiate it. And we sort of know that. Some people might have heard about automatic differentiation. It's used heaps in, someone was telling me it's used in machine learning and all this. But any function, most functions you can write down, you can differentiate. Bessel functions, all of that stuff. You can differentiate this function. So you can basically, so everything in the matrix is differentiable. So this matrix will be differentiable. So you can go out and you can head off into the complex plane and find some zeros of this, and then you've got an integral in the complex plane over all frequencies. You start closing contours, you start projecting onto poles, and you can start constructing this approximate solution. It's kind of an incredible technique. It's not, and it's so general, it just appears everywhere. Every single problem is linear. It just appears. Then again, these are these leaky modes and all of that. If you type leaky modes in, you'll find thousands of papers all about it. It's just a super common phenomenon. And then you get this, you can write down these approximation formulas near it, and you end up with this M1, which I don't know why I've written 1. It's a derivative of M at the point. You end up with the derivative of the matrix. As it's a Taylor series, it's probably not totally surprising. And you can calculate that, like I said, you use packages for automatic differentiation. I was too silly to use those. I just did it numerically. But this formula is kind of neat, and you end up with these. It's very similar to what you get for a self-adjoint matrix, where you get these projections, but you end up with two different vectors. The vector of the adjoint of M. So because the system is starting to lose self-adjointness, you've lost that structure, and so you go to this non-self-adjoint matrix theory. So yeah, and these sorts of formulas are kicking around, but I think in this case here that I probably wrote this down myself. It may have seen something similar to it, but I can't quite remember. I certainly don't remember copying it. The notation's clearly all mine. All right. And then you end up with this crazy kind of approximation that you can derive into the time domain from this formula by resubstituting it. This certainly is my own expression here. All right, so let's just believe that's possible to do that. And I'll just show you an example here. Hopefully it's going to play. Here's a brilliant example. Okay, hopefully you can see this. So it's 4 cylinders, scattering, a wave equation, scattering by 4 cylinders. So it's fairly simple to solve this in the frequency domain. It would have been groundbreaking research like 30, 40 years ago. Graphs addition theorem or something. So the wave comes in, bounces around. Lots of people are doing these cylinder problems, actually. You'll find loads of them. This is just a very super simple example. So what happens is the wave hits that, and there's inside the cylinder, and then you can see the wave on the right. The generalized eigenfunction method is actually the full solution. This is an approximation, a one-dimensional approximation from that funny formula I showed you before. What happens, the wave whizzes past, and it leaves behind it this excitation in the cylinders, and this excitation is almost trapped. It's very, very slowly radiating energy out. But the gap between the cylinders is actually not that small, but this thing's completely out of phase at the cylinder, so it hardly has any displacement across this gap. And so what happens, eventually the system settles down to this one-dimensional system, and the formula, the projection onto that mode is given by that horrendous formula that I gave you. But that's essentially just kind of normalizing the this leaky mode and projecting onto it. These leaky modes are really, if you ever do study them, you're going to freak out because you'll find that they grow out to infinity. So that just seems top. They don't, the energy just keeps growing to infinity. So you think that's really stupid, because why would I want to approximate my function by something that grows to infinity? But it turns out you do. And I don't have time to explain why. I'll move on, okay, because time's running out. But there is a good reason why that does work. That is logically what you want to do. And you've crossed over. You think about your Laplace transform. I will give an explanation. You're stuck on one side of the plane, and you're not allowed to cross into the other because the e to the st doesn't converge, right? In your Laplace transform, there's that Bromwich contour, and you're stuck on one half. You can analytically continue, and you just go into that forbidden zone. And when you go into that forbidden zone, that's what you're doing here. And it turns out that actually is how to approximate the solution, but with this proviso that they grow. You can see how well it works. I'll try and show these movies. These movies really illustrate it. This is a much tougher problem to solve. So I'm probably the only person to have solved this problem, certainly by this method numerically. So you start with some initial condition inside the cylinders and you release it. Most of that energy runs out, and then you're left with this, with a single mode approximation. And you've essentially, it's like you've taken that initial condition and you've projected how much of it's on this mode. That's what you do if it was self-adjoint. And if it's non-self-adjoint, that projection becomes more complicated because how you do that projection. Okay. But this singularity expansion method, this mode is very accurate here, right? You believe these two are agreeing. I mean, I could have faked this, but I didn't. But this function does grow out to infinity. So that this approximation is only valid inside this region. Okay, and it's valid in a finite, ever-growing finite region, in fact. That's another story. All right, on to the next problem. So we can do 9 cylinders as well. So we can do any number of cylinders actually, but 9's kind of cool because you can see what's going to happen here. You're going to end up getting a trapping. There's 4 trappings now, right? So the single hole that was there breaks, and you can it breaks into 3 different values. One of them is a double because there's 4 kind of solutions that you can break from symmetry, and of those 4 solutions, 2 of them are the same. So they're identical under rotation. So now this is actually a 4-dimensional solution, and you can, I probably haven't imposed enough symmetry breaking on it, but you get quite interesting effects where these vibrations, they're much more stuck in the cylinders. They don't radiate as energy anywhere near as quickly as the one with 4, right? You can imagine that it's harder for the energy to get out. If you started increasing it, it'd take forever to get out. But they can start to move around the structure. You can see it here a little bit. It's starting to appear over here. Right, it's starting to move from these 2 over to these 2. All right, Okay. I'm not going to run over time, I promise you that. So obviously, if anyone's worrying about that, we'll see a few more movies. We can do a few more examples here. This is the, so that was just the wave equation in 2D. So we can now go to waterways. This is my interest and how to apply it into here. So this is the boundary condition for the waterway problem. So you've got Laplace's equation with some boundary condition. Everything happens on the boundary here. It's a little bit trickier, and the waves are dispersive and all of this stuff. All right, I'm not sure how important all of this thing is. You end up with a similar sort of structure. I'll just try and show you a few movies of it. There's that formula is almost identical to what we got before, right? That just falls into the same structure. It's all about self-adjointness, and self-adjointness is all about preservation of energy. So a system that conserves energy, it's going to have, if you then say, we define some in a product, which is the energy, then it's going to, the evolution equation is going to preserve energy. So that means that the system is going to have to be, the underlying operator is going to be self-adjoint. So, and then that self-adjointness gives you a normal structure. There's a spectral theorem about self-adjoint operators that tells you that how to construct, that you can make these. It doesn't tell you how to make them, and it's a bit more, it's a bit complicated. Here's an example here, though, for the waterway case. You get a wave going out. There's not a lot of, there's a lot of maths, and there's not, the time-dependent problem's not super well studied. And sometimes it's not super important, but there's a few reasons why this method could be really useful, I think. See that one there. Interesting what happens here to this problem, you know, you get this near trapping, and so the wave here, the water can kind of flow under here. And the very long waves, they're quite deep, and they hardly see this dot. But the short waves, this is quite impenetrable, and you end up waves sort of, you know, trapped and bouncing between. You can start to see here how you're gonna, the thing's starting to go from being, you know, if these stretched out to infinity, the problem becomes compact. So you're getting this transition. Love watching these movies. All right. And then if I make the dots larger, you get a slightly different behavior. There's going to be more trapping here. It's interesting. One of the funny things about this method is that you've done a lot of, you've numerically truncated the problem. You can't cover an infinite number of frequencies. You can't have an infinite number of points. So the method is at its least accurate at t equals 0, which is very strange, right? If you think about it, you know that you tell the system what the value is at t equals 0, and then you ask it to calculate the value at any time, including t equals 0. There's no time stepping. It's accurate for all time. It'll count the equation, and the matrix multiplication will just calculate it. You tell it, I want to know the solution 10 seconds later, it calculates it. So when I create these movies, I just ask it to calculate one time after the other. I never tell it what it got before. It's not interested in that. So when I ask it to calculate at t equals 0, right at the start, it doesn't necessarily have to produce the actual answer. And you can see there's a few little twiggly bits here. So you can actually tell how well your system's working. You don't need to, it's not like, you know the accuracy of the system, because you can just see how accurately did I do the t equals 0 when I told it what the system was, what state the system was in. I should have probably pointed that out. Yeah, and this is another problem with some merge dots. Okay, if you don't think of water waves, you imagine this is the fluid of the water. These are two sort of barriers here. So it's going to be nowhere near as strongly trapping. The short waves actually can flow over here, and it's the deeper ones that get stuck, and but they slowly radiate out, sort of a lumps of energy stuck between. Quite interesting. Okay. And then this is another way to look at the problem here. So this is where you've got something that can actually move. And I'm sending in, there's another way to think about the problem, is I'm asking the question, I send in all these waves from infinity, and I want to produce a certain state, an initial condition at t equals 0. You can see this wiggliness is because of numerical error. So that's another way to think about this, the problem I've solved. Because I said to you, I want to start in an initial condition and let the waves radiate out and the system evolve in time. But the other question is, it's an equivalent question to ask, what ways would I have to send in from infinity to produce some very strange initial condition? So you imagine these waves are coming in, they're getting scattered by this thing, and it's also rocking. And we want to try and arrange those waves in such a way that at t equals 0, it exactly produces this state. Like, have a look at this one here. So these waves are coming in, high frequency ones, and these guys, the high frequency ones, travel slower. They've been traveling for ages. So these complicated waveforms coming in from infinity. You can imagine this experiment in a wave tank, and then I want to produce at t equals 0 this crazy shape here, where I've got a Gaussian packet on one side and the plate displaced like that. So that's the same question that you're asking. One of the things about this method that could be really useful, I think, is suppose you had some system where at some point, say at t equals 0, you change the conditions that are you change the equation of motion for this dot. Like, instead of it being freely moving, you grab it, or you start to extract power from it, or something like that. And then you can keep time stepping in using the linear theory, which does work very well, but you'd have to using this method because it allows you to time step, right, from that initial condition. So you've got a system that at t was at some point changes dramatically, and that dramatic change can happen at an unknown time. You could send the system, you could send the waves in, and that comes back to that problem of the ice breaking. So this is the idea of the ice breaking problem. I won't talk about this too much because I'd like to just quickly touch on this SPH. So the idea of the ice, this is how we can try and solve that problem I showed you right at the start of the ice. So we can send the waves in, and then we can monitor the state of the ice, and then at some point, which we don't know, we'll only know when we solve the problem, the ice gets sufficiently bent that it breaks. And then once it breaks, in the boundary conditions, the scattering problems change because you've now got 2 bits of ice and you can have scattering. And then we ask, how does it propagate forward from there? All right. And this is just a few equations, how this could work out. So I mean, this is actually a project I'm trying to do here, but let's show you this. So this is the problem here. So you can imagine how this would work. So we start out and we send in some wave pulse. Okay, this is the water wave, this is the ice. So this is the ship making the wave, right? Comes in and it hits the ice. So the ice starts to bend. And then at some point, it gets sufficiently bent that it snaps. And you can see that the bending is at the most, you know, there's a peak of where the bending of the ice is. So it's going to snap it. And then we continue to march the system forward using this method. We'd have to recalculate the solution based on where it snapped and then send it forward. But this is it's exploiting the structure that allows us to start from some initial condition and move on. So we feed that initial condition into the next problem. And we've also got this non-linearity, this dynamic braking, but we're still maintaining the linear structure. And here you go, here's the, you know what I mean? Like, so it's broken now. So I can't, I haven't actually got this thing at all working. It's on my to-do list. You can see here, here's the problem of, you know, with the ice where there's now a break. Okay, you can see here. All right. And the scattering problem is different. All right. So that's, you know, just to illustrate the idea how the method could be applied to some sort of new types of problems. And there may be other problems like that around. I'm sure there's, you know, different problems. All right. So the final thing I wanted to talk about is this smooth particle hydrodynamics. So this is a very, very different type of approach. It's very numerical, but it's a very powerful method. If you're not familiar with it, it's worth learning a little bit about it. And I've been working on this problem. So it's like it's the far end of CFD. So if you know anything about CFD, you know there's this software package called OpenFoam, which is very, very powerful, that uses a volume of fluid method, which is also very powerful. And like everything, everything's a compromise, because so smooth particle hydrodynamics is more general than OpenFoam. It's more, but it's more computationally demanding. So you could, it might be possible to solve the problems that we're going to describe quite well in OpenFoam, but neither of the problems are able to cope with the problem that we want to solve, which is where you've got this flexible structure, like something that can flex like ice. So we've been working on extending SPH to the case of this flexural body. And this is actually one of the, there was a postdoc who was working actually on another project, but he was very, very good on SPH, and I got him interested in this, been quite successful. So the way SPH works, I should really have it a picture. That consists of particles. The particles don't describe particles of water. What they describe is particles that represent the solution. So you basically, the solution is represented as a huge number of particles that carry the solution with them, and they're allowed to overlap, and then the solution adds up. Like the solution is carried not just where the particle is, but around with them. But it's basically it's a mesh-free method, so that those particles can move, and it's not tied. It doesn't involve remeshing or anything like that. And the particles are kind of pushed around by the fluid motion. So you can have places where there's no fluid, and then the particles can carry the fluid in. It creates all kinds of other problems because it's not clear to work out what the free surface is and how to track it and all kinds of stuff. And you can get terrible numerical instabilities and things like that. But the method works really well. And it's used to do, you go along to see these modern Star Wars movies. You went to the old ones, old Star Wars, okay, and the old ones are better. They were always in deserts because there was no water. Whereas now there always seems to be endless water and waves breaking and all kinds of stuff. But that's because the special effects can simulate that using SPH. It's heavily, heavily used in the TV, in the movie business, back more than anywhere probably, because it's super accurate. Sorry, it's not necessarily super accurate because we don't really know how to quantify it scientifically, but it looks really good, which is all that matters. Nobody cares if the waves don't. No one's sitting in the thing going, that wave doesn't quite break like that when you're watching Star Wars. Okay, and then there's this the ice. We allow the ice to be elastic. So one of the reasons for this whole modeling that I found for the ice that's really great is that you can use the same particles for ice as you can for the fluid. You just say you're a bit of ice, and then you're going to obey the equations of ice. So you're going to be elastically bound together. And of course, that allows us to do one thing, which is my goal of all this work, which is to have a model which allows melting. So you can think about what's going to happen, right? The particle of ice is going to, something we've got to do is add another quantity, temperature, and then this particle of ice can melt, and suddenly it can go from being a solid to being a fluid. So it sounds like a great idea, and we have managed to start doing it. It's just, and here's the equation for the heat transfer. So you've got to add this equation in. One of the things that's really annoying is ice is actually, perhaps annoying is the wrong word because it supposed to be a catastrophe. The latent heat of melting of ice is massive. It takes as much energy to melt a gram of ice as it does to boil it, which is, and it's why ice, snow, glaciers, things don't melt in a flash. When this latent heat was discovered, the person who discovered it felt like this was, so lucky because he sort of imagined what would happen in the Alps if the ice just suddenly went from ice to water and just flowed down, in 10 seconds on the heat. So, but it's very, very high for ice. It's much higher than it is for things like butter or for other oil or, I don't know, lard or some sort of thing, that other solids, or for iron or copper for that matter. So the latent heat is enormous for water. So that means that you don't get a lot of melting. So and so we've got to simulate. SPH is very, very costly. It's going to cost us a lot of computer time to simulate even a few seconds, and there's not going to be a lot of melting in that, unfortunately. But let's have a look at it. Yeah. This is super important, you know, and we're allowing the particles to move from one to the other. So here's a little picture of the numerical results. So this is a piece of ice. We want to see how it melts. So the ice is at -1 and the water is at 20. So this is pretty warm water. So this is just a proof of concept, really, what happens in 300 seconds. You start to get this, and the ice is able to flex. I'm not sure the flexion of the ice is super important. We probably added too much into this model. But the ice starts to flex, and you get water streaming across the top, and you get this cold water starting to appear. You can see the process of melting and it's enhanced. And one of the things we're interested in is how much of a role waves play in the melting of ice, because the waves push water around onto the surface. They do all kinds of things to it, and we believe that that has an effect. We're trying to quantify that effect. But, you know, it's a bit like the spherical cow. We've now got this problem. If we ran it with water that was close to equilibrium, there's only a tiny temperature difference. The melting would be really slow because of the amount of energy that it needs to take off. Right. So it's kind of surprising. If we let this amount of fluid come to equilibrium, this one block of ice here would cool the fluid significantly, right? Because it's about 100 degrees of heat to melt that. It can lower 5 times its volume from 20 to 0, if you like. And there's a picture of the water temperature dropping, and you can see the effect of it. And then the most interesting thing here is how much effect the waves have. So if you have no waves, you just get the slow convective cooling. And if you have waves, you get much more cooling, much more cold water formed. So that's one of the things that we really wanted to show. So it's an interesting thing, and there are people interested in the way that waves create, the way the waves melt ice. All right. This is something here showing how the melting is greatly increased. So this is from this SPH, and there may be people who are interested in this model. There are open source SPH. It's not quite, it's probably an understatement. It's not as well developed as some of these other open source projects like OpenFOAM, for example. And there's probably not a consensus about that OpenFOAM sort of dominates the volume of fluid market. All right. It's another picture here just showing the different effects of the waves on the melting. And there's this picture of the temperature drop in the melting amount melted. Okay, highly correlated, not a surprise there. Yeah, so there we go, the SPH method. It's not this, like everything, you think this is going to solve every problem, but you run into all the problems with the computing. It takes like millions of unknowns to simulate that. And then you've got to time step that, and you're constrained by the time step. All right, I'm conscious of the time being finished. I don't want to go over time. So I'll finish there. Thank you very much. These are some publications. This one here is actually to be submitted, but it's this is the one that I showed you the figure. It's under review, but we've had very positive reviews from the physics of fluids, so it will be accepted, I'm sure. All right, I'll finish there. Thank you very much.
Thank you, Mike. Thank you for the nice talk on time dependent problems in very static. We observed the EM and SCM methods. The problems and then SPH method is discussed.
Directly.
Yeah, but honestly, not. So now the session is open for the question.
Online people can ask their own.
Okay, even the those who have joined us online, they can ask the question. They can simply type the question.
No need, sir. Directly they can ask. Already it is, and is it not?
Any question?
Where sir? Where sir?
Yes, sir.
Yeah.
No,
Yes,
sir,
yes,
no
in fact,
question. Thank you very much, Professor Mai, for your nice talk. I have no question, sir.
Okay.
Okay. There's no question, then let's take the speaker, Professor Mike. Thank you very much for your nice talk. And can we have a round of applause for the speaker?
Okay, and thank you. Sorry, I haven't been able to join more because of that. I'm in the UK. It's much better being in Australia because I was, it was late in the evening. I'm not one to get up early, but thank you very much.
Thank you very much for joining us.
Can close it.
Hi, Professor Mike. Thank you very much. Here, Dr. Behera. Okay, Rita sir. Bye-bye,
Thank you for
sir.
inviting me. Thanks a lot.
Yeah, bye.
Yeah, thank you. How's your thing going on there, London?
Good. Yeah. I saw some Santa were here.
Oh, when you are coming to Australia? Hey,
Um,
you are coming to IIT Kharagpur, na?
hopefully, yeah.
Yeah. Okay.
Yeah.
Okay, thank you. Have a nice day.
Yeah.
Bye-bye.
Okay, Dr. Mehra, you can join us tomorrow for the sessions. It will be good.
Okay, sir. Rita sir, thank you very much.
Yeah.
Siba
Thanks a
sir,
lot.
bye-bye, sir. Thank you.
And now,
Thank you all. Bye-bye.
Yeah, thank you, sir. Thank you so much, sir.
uh,
Thank you, sir.
Yeah, stop.